My name is David Hicks. I'm a postdoc at the Center for Autonomous Materials Design at Duke University. And so today in this session, as Cormac said, I'm going to talk more about the structural analysis tools that you can perform with AFLOW, and also generation of coordinate models with AFLOW. And so I'm going to be briefly covering 3 modules, so kind of a high-level overview. First, we'll start with AFLOW-SYM, so how you can calculate crystallographic symmetries with our software. Then I'll also talk about this prototype encyclopedia, so basically generating these materials that Cormac mentioned. And then also the last module will be AFLOW-XtalFinder. So again, it's related to this idea of comparing crystallographic structures to identify duplicates, but then to also find structural prototypes. And so just to kind of motivate this in the context of this camp, so the idea here is that with tools, these structural tools in AFLOW, we can use them to potentially aid machine learning training. So for example, there are a lot of different structural tools that I'll try to cover that you could actually use as descriptors, specifically symmetry descriptors, that you could potentially use as feature vectors that could be used to train machine learning models. And in general, using structural analysis tools can be or can be more efficient than actually performing a calculation. So these are DFT calculation. And so using this is a nice way to train your ML models. And then the other big part of this session is going to be crystal prototype generation. And so the idea here is that you can take a backbone crystal structure, and then you can decorate it with different elements. So here's 3 examples here. And so you can do this automatically with the AFLOW software, and so you can generate many materials essentially automatically. And then you could feed it into your ML model, and Corey's going to show the AFLOW ML model or API that has different models. And so you can basically have a programmatic workflow to basically generate hypothetical new materials, and then also predict what their properties might be. So this is kind of the motivation behind this session. And again, it's going to be a very high level overview, and I'll show you some online tools. And then at the end, I'll show, or I'll say that you can download AFLOW, and you can look at some of the other functionality that you can use. Okay, so the first session that I'm going to go over, or topic, is AFLOW-SYM. So this is a symmetry software that we developed that determines the invariance of a crystal under transformation. And so this will determine or find symmetry operations such as mirror planes, rotation axes. And from this, we can get common symmetry descriptors such as the space group, Pearson symbol, Bravais lattice, Wyckoff positions. And again, these could potentially be used as descriptors in a ML framework. And so I just wanted to highlight some of the, I guess, technical details, because I think sometimes we take for granted, people may think that, all the symmetries are tabulated, what is really the difficulty here? And since we're working with real materials, I kind of wanted to show what the hurdles that we have to overcome, which we do in AFLOW-SYM, so that way you can do this automatically and just use our software out of the box. So just to highlight essentially how we determine symmetry elements. For example, let's say that we have a crystal structure. So in this case, just a set of atoms. And we want to know whether or not this set of atoms has 4-fold rotational symmetry. And so computationally, what we do is we take this set of atoms and we rotate it via the symmetry operation. And then the question we have to ask ourselves is, does this, when we rotate the atoms, do they map back onto themselves? And since we're working with real materials, we're not necessarily working with ideal positions. And so these are essentially the 3 scenarios that we can encounter. The ideal situation is at the top here. So if the original atom positions and the transformed atom positions map exactly onto one another, then we would say that this is a mapping in our crystal. On the other hand, we may rotate at the bottom here. We might rotate and we may not land back on atom positions. So obviously in this case, we don't have 4-fold symmetry. But the most realistic case is actually in this middle scenario here, where when we rotate, we're not exactly lined up on the original atom positions. And so the question becomes, should this be a mapping or not? And so since we're working numerically, essentially we have to employ a tolerance threshold that says, okay, we're within this distance. And so we would say that, okay, it's close enough to be considered a mapping. And so this would be an isometry of our crystal. And so we essentially have to take all of the original atom positions and compare them to the transformed atom positions and check if they're all below this distance. But again, since we're typically modeling inorganic crystals, so we have periodic boundary conditions. And then also, if you're familiar with some of the modeling techniques that you can use, you can represent coordinates in direct or fractional coordinates. And those, depending on which space you're working in, you may not be using a uniform metric tensor. So you may not be in a uniform metric space. And so there's a lot of details that I'm not really going to cover, but basically I wanted to highlight some of the algorithm improvements that AFLOW-SYM has, and then I'll compare it to actually some of the off-the-shelf packages. So 3 things that I wanted to highlight is, it looks like there's a question in the chat. So is there a good number for global tolerance to work on all of the structures? That's a very good question. And actually that's this last part here. So I'll get to that in a second. And if I don't answer your question, feel free to let me know, but a great question. So the 3 algorithm improvements that I wanted to highlight is, again, related to this mapping procedure. So again, if you're working in different spaces, if they don't have a uniform metric tensor, then you need to be careful when you're doing mappings. And so if you're interested in this idea, I would encourage you to read the article we wrote. We have a long discussion on this, and it's actually quite interesting. The other thing that I wanted to mention is, so if you're working with other software, typically you have to have an input tolerance. And so in AFLOW-SYM, we actually have an adaptive tolerance scheme. And so I highlight this here with this tolerance number line. And so in this case, if we have tighter tolerance symmetry thresholds, then you might observe lower symmetries. So for example, if you use a tight tolerance threshold, you might observe monoclinic symmetry, while if you use a looser tolerance criteria, you might observe higher symmetry, so FCC. And this is actually a real system that we saw in the ICSD. And so, but what I want to highlight here is this void here, or this confusion region is what we call it. And this is a case where we found incommensurate symmetry. So maybe we found 49 point groups, which is impossible based on crystallographic rules. And so instead of throwing errors and having users play with the tolerance, basically we have an adaptive scheme that does a tolerance scan to basically find consistent symmetry at a new tolerance value. And so going back to one of the questions in the chat, is there a good global tolerance for essentially all systems? And we actually did a large benchmark, again, on the inorganic crystal structure database. And we found that essentially this epsilon tight is a good metric for tolerance values for determining symmetry. And it's essentially system specific, so it considers the nearest neighbor distances, and then it essentially scales it. So that's what allows us to basically resolve crystal symmetries that cater to any system that we may encounter. So excellent, I'm glad that answered your question. And so in general, we typically use this default tight tolerance value, and then you can also use this secondary default, which is this epsilon loose. And what I want to highlight here is that if you work with other symmetry packages, sometimes you have to specify multiple tolerance values. So for certain rotational symmetries, you might actually have to have a separate tolerance value. And as a user, this can be pretty cumbersome, but what's nice about AFLOW-SYM is there's essentially one single global tolerance that you can either specify it if you like, or you can just use the default and you get high consistency results. And so your next question might be, okay, so I've introduced these algorithm improvements. How do we compare to the off-the-shelf packages in the community? So if you're familiar, there's other packages such as FineSym, Flatten, and SPGlib. And so we did this benchmark where we took inorganic crystal structures or structures from the ICSD, and typically they report the space group that they measured experimentally. And so we compared the experimentally reported space group to the one calculated by these particular software. And here we're plotting the mismatch. So when experiment and the code did not agree. And so basically the taller these bars, the worse the package performs. And so in general, you can see across different lattice types, AFLOW-SYM has the fewest number of mismatches. And we also, you'll notice that some of these other packages have solid bars and dash bars. And what we did here is we changed their default tolerance values to kind of see if we could change, the results. And in general, you see that, okay, if you tune the tolerances with these other symmetry packages, you may be able to improve your results. But the take-home message here is that with AFLOW, you don't need to kind of play this tolerance game. In general, if you use the default tolerance that we have and and since it uses this tolerance scanning method and some of the other algorithm improvements that I mentioned, you can get high consistency results with limited human intervention. So there's a question in the chat. Any thoughts why the mismatch is generally largest for hexagonal lattice? So that's a great question. And I think it has to do with the six-fold symmetry. So a lot of the packages actually had tighter tolerance values. And for some reason, there was some of these other packages had difficulty characterizing, especially the six-fold rotational axis. And again, I think it's related to tolerance value. And so I think that's why there's this biggest divergence for the hexagonal systems. So, but yeah, great question. Okay, so I'll briefly highlight some of the things you can calculate, and then I'll show you some online tools that you can use to actually calculate these things. So with the software, you can calculate different symmetry groups for the structure. So if you wanted the symmetry group for the lattice, we can calculate that. We can also calculate the Brillouin zone symmetry, what's known as the factor group, the unit cell symmetry, and all of these other different groups that are discussed in crystallography textbooks. We can also calculate common symmetry descriptors. So as I mentioned, the space group, the Hermann-Magrian symbols, the Hall symbol, Pearson symbol. And we also are consistent with the international tables for crystallography. So this is essentially the de facto standard for symmetry in the community. And so we can actually represent crystals in this form, and in particular, the Wyckoff position. So we can calculate the Wyckoff position, so give you these multiplicities, letter designations, and representative coordinates. And AFLOW also has the engine underneath to basically, given a representative Wyckoff coordinate, it can expand that coordinate based on the symmetry, the particular space group symmetry. So there's that functionality in AFLOW. All right, so I think at this point, I'll go ahead and highlight some of the online tools that we have. So first, I'll be showing how you can actually upload geometry files to our online portal and actually calculate some of these things. And then also I'll show a visualization. I guess I can actually just show it here, but on every entry page in the AFLOW database, you can actually visualize the entry, and then you can also visualize the symmetry elements. So we've calculated all of the symmetry elements for this particular structure, and you can actually rotate it and actually see it in real time. So in this case, we're rotating about a particular fourfold axis, and we can see how the crystal maps back onto itself. And so we like this tool because it's a nice teaching tool. And again, if you're having trouble kind of visualizing a particular symmetry element, you can use this tool. All right, so I'm actually going to go ahead and navigate to the actual web page. So if you'd like to follow along, you can open a browser and just go to aflow.org. So we did this in Cormac's session. And then we'll go ahead and navigate to this AFLOW online section here. So I'll give everyone a second to do that. And it looks like there's a question in the chat. Can it happen that experiments give an average symmetry of the structure, but a computationally relaxed experimental structure give a lower or different symmetry? So that's an excellent question. Yes, indeed, it can happen. And actually, if we have time, I had some exercises, and there's actually an exercise where I ask you to change the tolerance value on the web page. So actually here you can see that we can upload a structure and we can change to one of these preset tolerance values. And so we actually see that in the example that the symmetry changes based on that tolerance value. And so in general, we've actually done some benchmarks, and we've done a few tests, and we actually see that when we have some experimentally reported structures and we have their space group, and we can actually see that we can kind of, depending on what our tolerance value is, we can actually map to the experimental structures, or actually be a symmetry subgroup of the experimental structure symmetry. So yes, we have seen that in some of our investigations. So, but great question. All right, so if you go to the AFLOW Online page, you can see that you can input a geometry file. We support many different file formats, so postcar, CIF, Quantum Espresso. So if you're using some of these other ab initio packages, you can do these analyses online. And so AFLOW will auto-detect the input. And so we have some quite a bit of online functionality, but I'm just going to highlight some of the symmetries. So you can calculate, for example, the space group, Wyckoff positions, Pearson symbol, and the different symmetry groups. And so we already have a structure loaded by default. So you can click on the space group. And then if you're familiar with the ITC, you can specify different settings. So setting 1 and 2 may toggle between hexagonal or rhombohedral settings. But for now, we'll just do the AFLOW standard. And if you click, then you can see that you can actually calculate the space group, and you get the labels, the number, and then also some additional information. So it looks like there's a question in the chat. So you're having problem accessing AFLOW Online. One thing that you could do is use the alternative link that Cormac mentioned. So I think it was, yes. So you're using, yeah, so you can either use the one that was put in the chat, or you should be able to use yes, so this one here, let me put it in the chat. If this one isn't working for you, you can try this one as well. So it could just be that since we have quite a large group, maybe our web page is kind of getting hit by multiple users. So I would try that. So you can also calculate Wyckoff positions, for instance. And again, you can calculate that. All right, so it looks like it worked for you. Excellent. So you can calculate Wyckoff positions. So you get the space group, the ITC cell, and then the Wyckoff positions here. And then the last thing that I'll highlight, so you can also do Pearson symbol, and then also the different symmetry groups. So if you wanted the explicit symmetry operations, so let's say for the crystal point group, you can actually do this. And in this case, there are 48 point group operations, and it gives them to you in the different representations. So rotation matrices, axis angle, etc. And then if you like Python, which I think we've actually seen a lot of this in the past week, we also have a JSON representation. So if you're familiar with that, you can actually do these analyses and we can get a JSON response back. And so again, this is nice because you can easily integrate it into a Python framework. And at the end, I'll show that we actually have some Python modules that if you were to download AFLOW, then you could actually use this programmatically and use the Python module and kind of integrate it into your own workflow. So I won't go through all of the tools here, but I would encourage you, if you're interested, to kind of play with these tools and see what you can calculate online. All right, so maybe it's a good time to see if anyone has questions, or maybe I can do the poll. So I'll go ahead and relaunch the poll. Are people following the lectures? And if you need me to slow down, feel free to ask. And again, if you have questions, feel free to post in the chat. So someone has a question in the chat. Are these pulling pre-computed DFT calculations? You can do pre-DFT or post-DFT. So in this case, actually, I'm not exactly sure where this particular structure came from. It could be pre or post-DFT, but actually, when we do when we calculate things in the AFLOW database, typically we do a symmetry analysis before, so pre-DFT, and then also post-DFT. So for instance, it may relax to different symmetries upon relaxation. And so that's something that we actually can see in the database. And we actually have API keywords that Marco is going to show. And some of them are, space group original, so before DFT, and then space group relax, so after DFT. Okay, so it seems like maybe about 70% are following. So again, if you have questions, feel free to ask. So somebody also has another question. They saw magnetic moment unit cell calculations. Are there any publications you would recommend where the magnetic properties are calculated? So we do calculate, when we do our density functional theory runs, we do have spin polarization on. Typically, we look at some of the more simple magnetic orderings. So I would encourage you to look at our AFLOW, I think it's the AFLOW standards paper. Maybe one of the AFLOW team members can correct me if I'm wrong, but I think that one might be a good one to look at. But then you can also use the symmetry tool to actually calculate what we call the magnetic crystal spin symmetry. So if you specify the magnetic moment here, then you can specify collinear, non-collinear spin and see how that changes the symmetry. Yep, no problem. All right, so I'll go ahead and navigate back to the slides. All right, so that was the first module. The next one that I'll talk about is the Prototype Encyclopedia. And so the idea here, as Cormac mentioned, is that we can generate crystallographic structures with the AFLOW software. So AFLOW has these built-in prototype structures. So for example, we have some common ones such as the Heusler, half Heusler, and also some other ones that we found in the literature that we thought were useful or that were very prevalent in nature. And so the idea again here is that we can take these backbone structures and decorate them with different elements to generate hypothetical new materials that we can either run simulations on or also feed them into a machine learning model to see what properties come out. And so we currently have 1,100 prototypes available online via our Prototype Encyclopedia. And you can actually see where we got the structures and you can actually generate them online. And so this is an endeavor that we've been working on for the past couple of years. And so this is the AFLOW Prototype Encyclopedia. And you can basically find, we have a web version. We also have a document version. So basically you can look up these prototypes, find all their different symmetry characteristics, visualizations, and things like that. And so we have this in volumes. So part 1, part 2, and part 3 giving us a total of over 1,000. And we're already working on part 4. And so we'll probably essentially add another 600 or 700 in the next installment. And so one thing that I want to highlight is with this encyclopedia, we also wanted to have a scheme to classify and characterize crystallographic structures. And we wanted to come up with a descriptive label that we could use for generating, but also that as a user, you could kind of see when you look at the label, you have an idea of what the structure may look like. And so we came up with this AFLOW prototype labeling scheme. And so here's the label here, and you can see that it's essentially a string separated by underscores. And so here in the first field, we have the reduced stoichiometry of the prototype structure. Next is the Pearson symbol. Then it's followed by the space group number. And then the subsequent fields are the Wyckoff letters associated with each species. So for example, species A has Wyckoff letter B, and species B also has Wyckoff letter B. And so this corresponds to the Wart-Site structure. But from this alone, this doesn't uniquely designate a particular crystal structure. And that's because we have degrees of freedom based on the symmetry. And so here are the symmetry based degrees of freedom. So we need to specify lattice parameter A, C over A, and these Wyckoff coordinates, Z coordinates. But what's actually nice about this particular designation is you can actually tune the degrees of freedom to get slightly different structures, but while keeping the underlying symmetry. And so again, this is a very powerful prototyping tool because as a user, you can specify a label and essentially an infinite number of parameters to generate many different structures just with this one label. And so this is essentially the prototype generation scheme that we have. And so it's very useful for generating multiple structures. All right, so at this point, I'll go ahead and show the online tools. So basically how you can see these structures online and actually generate them. So again, In the PDF, I've highlighted some of the characteristics, but let's actually go ahead and navigate there. So again, if you go to aflow.org, and again, if you scroll down, as Cormac mentioned, we had this prototype encyclopedia icon here. And so this will take us to the Encyclopedia of Crystallographic Prototypes. You can see that we currently have over 1,000 prototypes here. And so you can search by different characteristics, such as the space group, Pearson symbol, the structurberisch designation, if you're familiar. And we also have some prototype indices as well. So for example, you could go to the space groups. You can search by space group. And then you can see all of the different structures that we have in each space group classification. And so we also have some basic search functionality. So if you actually hit this search page, you can search by name, space group, Pearson symbol. And so for example, let's go to a particular entry page. So let's go to perovskite. And so if you hit enter, you'll notice that we actually have quite a few perovskite structures. So the cubic, post-perovskite, double perovskite. And so let's go ahead and actually click on this first one. So this is the orthorhombic perovskite structure. And so for each prototype in the encyclopedia, it has its own corresponding prototype webpage. So of course we have a visualization, and we have some JML buttons that you can kind of change the structure. We have the prototype information. So basically this was the common material, a common material that exhibits the structure. So CATI03. This is that prototype label that I mentioned. Some other symmetry and the structurberisch designation. And then this is the prototype command. So if you are working with the command line tools, which we won't be showing today, but if you were working with these tools, then this would essentially be the command that you would run via the terminal. And we also list some of the compounds that exhibit this structure, some comments, and then also the units or the lattice vectors in the primitive form, and then also the basis vectors. And again, you'll notice that these are actually in symbolic notation. And so they are actually given in terms of A, B, C, and X, Y, and Z. And so again, this highlights this idea that you can change these internal degrees of freedom to generate a new structure that is in keeping of this symmetry. And then we also have some references where we found the structure. And then at the bottom, we actually have this prototype generator. So here you can change the degrees of freedom. So A, X, Z, et cetera. And you can change the species. And then you can generate a geometry file. And we support different output formats. So for example, you can use VASP. This would give you a VASP postcard representation of the structure. There's also Quantum Espresso. And there's also SIF, for example. And so you can see the different ways that you can represent this particular crystal structure. And so if you're interested, I would encourage you to kind of explore this page. You can see what different prototypes we have. And you can potentially play with the degrees of freedom and generate crystal structures. So if there are any questions, feel free to post in the chat. And the idea here, again, just kind of relating it back to what Cormac said, is that when we're somebody asked, are we always running more materials? And yes, we are. And essentially, this is how we're doing it. This is one way of how we're doing it. We're basically decorating prototype structures and calculating their properties, and we're adding these to the database. And so typically, we're trying to find structures that are experimentally reported by the community. And we also have some hypothetical structures that were found in theory works as well. All right, so I have one last section that I'll go through. And this is the XtalFinder module that Cormac had mentioned. And so just to give a little bit of a motivation for this particular module, so as somebody already asked in the, looks like we have a question. So once you generate a new structure, can you use AFLOW to do DFT and see if it is a valid structure? So yes, you can actually generate, so using this tool, the prototype tool, you can generate the structure. And then we actually have some machinery to actually generate an AFLOW-in file. So I think Cormac mentioned that at the beginning, but basically you can generate an input file for AFLOW to do this automatically. So it'll run the calculation if you have a DFT license for one of the ab initio codes. And then, so basically you can perform the simulation. And then for, when you mean valid, if you mean if it's maybe thermodynamically stable, then there are tools such as the AFLOW Convex Hull app that kind of gives an idea of thermodynamic stability. So, but yes, there is machinery to generate the structure and run a DFT simulation. Unfortunately, we won't be doing that in this workshop. But if you're interested, we do have, as Cormac mentioned in the AFLOW schools, we talk about that a little bit more. So if you're interested, feel free to check that out. Okay, so a little bit of motivation behind XtalFinder is, as we saw previously, there may be, for instance, multiple silicon carbide structures in a data set. And so we want to be able to have a tool that can basically mitigate duplicates. So we can find these duplicates. And this is important for data mining and statistics, and also for machine learning, because if you have duplicates in your training set, that can bias your machine learning model. So that's one reason we want this type of tool. The other is that we want to identify prototype structures. So again, back to this prototyping idea, we want to find unique backbone structures so that when we're trying to find or discover new materials, we're working with unique set of structures. So when we generate them, they'll hopefully be unique upon relaxation as well. But since we're working with crystals, it's a little bit difficult because there's different lattice and origin choices. And so this can obfuscate similarity. So for example, if you see these three structures here, they're actually the same crystallographic structure, so the same bulk structure, but just in different representations. And so this can kind of make comparing structures by hand very difficult. So we wanted to have a routine that can do this. And so this is where AFLOW-XtalFinder comes into play. And so the first thing that I want to mention about XtalFinder is that we have this automatic prototyping tool. So again, related to this prototyping scheme, basically given an input structure, we can determine what the prototype is. So again, this label and these degrees of freedom. And again, related to this symmetry tolerance idea, depending on what your symmetry tolerance is, you can find different prototype structures. So again, for tighter tolerance values, you might find this prototype classification. While for looser, you might observe higher symmetry classifications. And so again, AFLOW can do this automatically and find a self-consistent prototype given an input structure. And again, so we find all of these important designations, and then we can basically classify the prototype structure. And again, we found, consistent with experiment, that this symmetry tolerance typically matches with experiment the best. And so that's the first part of XtalFinder, is this idea of taking an input structure and determining what its prototype is. So again, its unique crystallographic structure and what the designation is. And again, this is important because it's consistent with the ITC. It's in this tunable representation, so you can change the degrees of freedom. And then it's also generatable with the AFLOW software. So actually, if you feed in these degrees of freedom, you can actually generate geometry files just based on this information. So that's the idea of classifying prototypes, but then there's also this idea of comparing structures. And so there's a lot of details here, but I'm just going to highlight basically that with the XtalFinder software, you can compare structures based on symmetry. So this would reveal isopointal structures, so structures with the same symmetry. You can also do local geometric comparison, so you can kind of see around a particular atom, what does the geometry look like? And so this is like a local snapshot comparison. And then finally, you can do a full geometric comparison where basically you're mapping crystallographic structures onto one another. So it involves a lattice and origin search. So basically to find a commensurate representation that you can match structures and then analyze their similarity. And so this will tell us whether or not structures match onto one another or not. So again, this idea of duplicates versus unique structures. And so you can use your own data set. So if you have a set of structures, you can actually use the XtalFinder software to compare your own structures. But maybe you also want to check if your input structure matches to, let's say, something in the encyclopedia. And so you can upload an input structure and you can basically see if it's in our encyclopedia. We'll do the comparisons for you and we'll return whether or not there's a matching prototype, or whether it matches to something in the encyclopedia, and you'll get the prototype information. And in addition, you can also use your structures to compare them to the AFLOW database. So for example, you can take your input file and you can see if this particular structure exists in the AFLOW database. And so this uses the machinery that Marco is going to talk about, so the AFLOW search API, to basically grab all of the possible structures that may match to your input. It'll do the comparisons, and then it will return all of the structures that match to your input. So in this case, we had a rock salt, sodium chloride, and you can see that based on this input, we actually have, I think it's 27 entries in the AFLOW database. Here's their similarity metric, so how similar they are. And you'll notice that actually all of them have similar enthalpies. So again, this is kind of highlighting the structure property relationship between structures that are similar. They would be expected to have similar properties. So there's a question in the chat. Why are there duplicates in the database, like the silicon carbide example we looked at? So I think Cormac addressed this earlier. I'll kind of reiterate what he said, but especially in the inorganic crystal structure database, some of these may be experimental structures typically, and they may have been done at different pressures, temperatures, and they would report the geometry or the structure at those particular conditions. But when we do a DFT relaxation, we're basically doing things at zero temperature. And so basically they may relax to the same structure. And so that's why we may see duplicates when we're comparing structures after relaxation. But there are also some duplicates that are in the ICSD, for instance. And so that can also be where these duplicates come from. So again, that's why a tool like this, to compare crystal structures, we can use this to identify that, okay, these particular set of structures are related, they're duplicates. And then so again, you can kind of, if you're doing some data mining or post-processing, you don't need to take all of these duplicate structures. You can just take a representative for your analysis. Okay, so I'll briefly highlight some of the online tools. And then I think in the interest of time, I may not go through the exercises just so the other AFLOW folks can discuss their sessions, but I'll go ahead and go back to AFLOW Online. So again, if you go to aflow.org, and if you go to the AFLOW Online tool, so some of the XtalFinder, functionality, some is under Symmetry. So if you want to define that prototype designation, that's under the Symmetry section here. You submit, and you can see you get the label, degrees of freedom. In this case, it's only 1. And then, for example, if you wanted to compare this particular structure to the database, you can do compare to database. And so this may take a few seconds because we're essentially taking the input structure and comparing it to all of the entries, or we're comparing it to the entire AFLOW database. So we have to grab the relevant entries and then compare. And so you can see based on our input structure, there are 4 duplicates within the AFLOW repository. And so you can basically see where these structures are coming from. Some are ICSD entries, and others are from the prototypes that we've been developing. And again, there could be duplicates either from the ICSD or because they relax into the same structure, to the same structure after a DFT simulation. Okay, so I think I might go through one exercise just together, just to kind of, because somebody asked a question about this idea of if you change the tolerance, kind of how does that change the space group? And also that can have an impact on or that can be related to what the experiments reported. So I'll just do this exercise, and then I think after that we might take a short break. But let's go ahead.
Do a poll too.
Sure, yeah. Let me go ahead and do a poll, and then I'll wait for the poll. Or while we're waiting for the poll, I'll also go through one exercise. So, all right, so the poll should be started, and while that's going, I'll go ahead and, so for this first exercise, it was basically to generate this particular structure via the online tool, and then analyze the space group by changing the tolerance value. So I'm actually just gonna copy this guy. It'll let me copy. There we go. Okay, so this is a particular structure, and I'm just going to go ahead and go to the bottom of the page. And I'm going to generate the structure based on the default parameters. And then I'm going to go ahead and copy it. And then if you go back to AFLOW Online, you can upload the structure. All right, and then what we'll do is, in this case, we're going to calculate the space group symmetry, and what we're going to change here is the symmetry tolerance. So tight, and then we'll do loose. So tight is one of the default parameters, so the minimum interatomic distance divided by 100. And so in this case, we get space group 119, but if we change it to loose, you'll notice that you get space group 227. So actually the space group, you found a higher symmetry. And so kind of relating that back to experiment, like somebody asked in the chat, basically actually this particular structure has different phases at different temperatures, and they exhibit different prototype structures. And so in this case, this kind of shows that you can, with this tool, you can kind of see, okay, if you change the tolerance, we might be able to get a symmetry that's consistent with what experiment reported. So, and this, for this particular prototype, we have a lot of comments, and we also actually comment on if you change the tolerance, you can kind of see how the symmetry changes and how that is, how that relates to what was found experimentally. So somebody asked in the chat, is it possible to generate distorted structures, say for alloys and structures with particular occupation on a particular Wyckoff site using AFLOW? So yes, again, we're not going to be discussing it today, but there's a partial occupation module. It's called AFLOW-POC, and Dr. Coriosis has been working on that. And so you can actually generate distorted structures, and basically how you control the site occupancy, you can control it per site or per species. And so you can kind of play with that. And you can also, if you know the Wyckoff positions, then you can do it per a Wyckoff site. So, but yeah, excellent question. If you're interested in that, there are some AFLOW schools that talk about that module in more detail. Yep, and then another question, are there ways to add defects via tolerance? I guess I'm not sure what you mean by defects. Do you mean actual defects in your crystal? Or I guess in general, if I understand your question correctly, I don't think you can use tolerance to kind of analyze defects in a sense, because basically you're going to take your whatever your input structure is, and it's going to use that symmetry tolerance to analyze the symmetry. And if we do like reductions in the cell, we're basically going to preserve the stoichiometry. So we're not going to throw out atoms if they map onto one another. We're only going to basically transform structures or map structures while preserving the stoichiometry. So we're not going to introduce any defects in that way. So I'm not sure if that answered your question, but yeah, in general, we're not introducing defects with the tolerance at all. Yep. Okay, so it looks like a majority of people were able to follow. If you have questions, feel free to post in the chat. I'll be here for a while to answer questions. Let me go ahead and close that out. And so I'll end my session just by saying that I've shown some online tools, but we also have, I know that in this workshop, you've been showing a lot of Python and Colab. And so you can actually do a lot of these tools in Colab or with Jupyter notebooks, but you have to install the AFLOW source code. And so there are instructions here. And so Marco Esters has been developing a lot of ways to automate this process for you based on whatever system you're working with. So I would encourage you to look at that if you're interested. And then if you actually want Python modules, you can actually run these commands once AFLOW is downloaded, and you can basically have this Python module so you can integrate it in your own workflow. And again, if you look at the AFLOW schools on our webpage, there's some tutorials about that. And so with that, I'll end my session. If there's any questions, feel free to ask. It looks like there is one. Can we generate data for different physical conditions, say temperature or pressure? So there are some thermomechanical simulations that you can do with AFLOW. So they're the AEL-AGL, and so that can kind of simulate different pressures and temperatures. So I would, if you're interested, again, you can look at some of the AFLOW schools in the past, and that's something that Cormac Torr has been working on. And so there's functionality in AFLOW to do that. So, but yeah, great question.